All right, we continue today with the discussion of inner product spaces and adjoint operators and certain operators with whose adjoints satisfy some additional properties. So let me just recall, first of all, where we stopped last time. So the adjoints, okay, recall. If T is a linear operator on V, where V a finite dimensional inner product space, okay, then the linear operator T star, a linear operator on V as well, satisfying the equation that the inner product of T of X with Y is equal to the inner product of X with T of star of Y. So satisfying this condition for all vectors X, Y in V is called the adjoint of T. Okay. And as we have discussed last time, there's a unique linear operator with this property. And moreover, first of all, it exists, assuming that the dimension of the inner product space is finite, and it's unique whenever it exists. Okay. All right, so we have this notion of a adjoint operator. Okay. And remember that it corresponds to the adjoint operation on matrices for representations. So, and if we have that the matrix representing, well, okay. So first of all, fix a basis here. So let me, if beta is an ordered orthonormal basis for V, okay, then the matrix representing the adjoint T star with respect to beta is the adjoint of the matrix representing T with respect to beta. Yeah. So we look at the matrix representing T, and then we take the adjoint of this matrix, which remember is just taking the transpose and applying complex conjugate. Okay, so we have this. Now for this to hold, it's important that the basis is, consists of orthonormal vectors. Yeah. Otherwise, it doesn't have to be true. So it's not true for an arbitrary basis, only for the orthonormal ones. Okay, so we have this. And let me just state a few properties of adjoints. So this is theorem 611 from 115a, which gives some of the basic properties of the adjoint operator. So let V be an inner product space. Okay. And assume that T and U are two linear operators on V. Then we have the following properties. So first of all, we can look at the linear operator given by the sum of T and U. Okay, so this is a linear operator. What is the adjoint of this? So if we want to know the adjoint of the sum of two linear operators, this is the same as taking the sum of their respective adjoints. Okay, so T star plus U star. This is property one. And these properties are easy to see, for example, from the matrix representation. Yeah, or you can check them directly from the definitions. Well, it's theorem 6.1 in the textbook anyway. So similarly, if I want to know the adjoint of the linear operator C times T for some scalar C in F, then this is the same as taking the complex conjugate of C and multiplying the adjoint of T. Okay, so this holds for any scalar C in F. Okay. Also, we have a condition for compositions. So if I take the composition of these two linear operators, T composition U, and I want to know the adjoint of this, then this is the same as taking the composition of the adjoint of U with the adjoint of T. Note that the order of the composition changes. So here it's the order. I first apply U and then apply T, but here I first apply T star and then apply U star. Okay. We also know that the adjoint of the adjoint is just the operator T itself. Okay, so if you apply the adjoint twice, you get back. So this you can just see quickly from the formula, for example, for the adjoint from this condition. And finally, we have the adjoint of the identity operator, IV, is just the identity operator itself. Which again is clear if you look at the matrices, right? Okay, so we have these properties of the adjoint operator. And let me just remark, so the same holds for matrices and their adjoints. So here we state all these properties for linear operators, but we have the analogous statements for matrices. All right. So this is some general remarks about the operation of taking the adjoint. So now we start actually connecting this with our discussion of linear operators. So the next topic, or the topic of today's lecture, is normal and self-adjoint operators. Okay. So these are two special kinds of linear operators on inner product spaces. So to motivate it, let's remember what we already know about diagonalizable operators. Okay. So assume I'm given T, a linear operator on a vector space V. Then we already know the following equivalence. We know that T is diagonalizable. Okay. If and only if V has a basis consisting of eigenvectors for T. Right? So we know that this is an equivalent characterization of diagonalizability. And this works just in a vector space. No notion of inner product or norm is used for this, right? Okay, so now consider a stronger condition that makes sense only when we have an inner product space structure. So assume that V has an orthonormal basis consisting of eigenvectors for T. Okay, so this is the strengthening of our condition, not just a basis consisting of eigenvectors, but moreover an orthonormal basis consisting of eigenvectors for T. Okay, and what we want to understand is what a property of the linear operator T corresponds to it. So T is question mark. Okay, so what should this condition be on the linear operator T? So for just for basis consisting of eigenvectors, we know it's diagonalizability. So here it should be something stronger, a priori stronger than diagonalizability, right? Because the condition on the right is stronger. We require an orthonormal basis of eigenvectors. So let's try to understand it. So in order to understand it, we need to study a bit how the eigenvectors of a linear operator behave when we have the inner product space structure, as opposed to just a vector space structure, okay? So let's see how it interacts with the inner product. And adjoints, as you will see, play an important role in these considerations. So let's begin with the lemma, which tells us how to find eigenvectors for the adjoint operator, starting with an eigenvector for T itself. So assume T is a linear operator on V, okay, where V is an inner product space of finite dimension, as usual. Okay, dimension V is finite. Now, if T has an eigenvector, okay, then so does T star. Okay, so remember that for general linear operator, there might be no eigenvectors at all. Okay, and here we're trying to understand how the eigenvectors of T are related to the eigenvectors of the adjoint. The very first step towards this understanding would be at least to ensure that if we have an eigenvector for T, then we also have an eigenvector for T star, right? This is like the absolute minimum of what we might want to have. And indeed, this holds. So let's start with the proof of this. Okay, so proof. So start with an eigenvector for T, yeah? Oops, 1 second. All right, so yeah, so suppose that we have V, a non-zero vector, okay, which is an eigenvector for T. So remember, eigenvectors are always non-zero, okay? And let's say the corresponding eigenvalue, let's denote it as lambda. Okay, excuse me. There's something going on with my headphones. Just 1 second. Okay, can you hear me well? Yeah. Okay, thanks. Yeah. Okay. Yeah. So fix an eigenvector. By assumption, we have an eigenvector for T, and fix the corresponding eigenvalue. Okay. Then for any x, a vector in V, we have the following equations. Okay. So we have 0, which we know is the same as the inner product of 0 with x. So remember that the inner product of 0 with any vector is automatically 0, okay? Is going to be, so sorry, before I write it, actually, what is the idea? So the idea is to use the only property that we know of the adjoint operator, which is this equation, remember, that the inner product of x with t of x with y is the same as the inner product of y with t star of x, right? That's the only we have, the only connection between T and T star that we have. So let's try to use it somehow, yeah? So, okay, so if I take the inner product of 0 with x, it can be written as the inner product of T minus lambda I of V with x, right? So why do I have this? Because look, if lambda is an eigenvalue corresponding to eigenvector V, then we know that T of V is the same as lambda V, right? Okay. In other words, this is the same as saying that if I look at the linear operator, T minus lambda times the identity, and I apply it to V, then this is equal to 0, right? It's just moving things around. So that's what I'm using here. So this 0, I can replace them by this expression. Okay, so this is 0 by assumption, taking inner product of this with x, right? Okay, but now I use the property of adjoint, right? So this is the same as V, inner product, and now we take the adjoint of that, right? So we take T minus lambda I adjoint, excuse me, adjoint applied to x, right? So this is just the definition of adjointness. And by what we just discussed, so theorem 611 that we just stated, okay, theorem 611, we just use these properties. So this is going to be the same as V, T star, so T is joint, minus lambda complex conjugate times I, because the adjoint of I is I, right? Applied to x, okay? So we have this. Okay, so what do we get? So, so what do we get here? So we get that, look again, so this is any vector in V, right? And for any x in V, we get that this product is equal to 0, right? So remember, inner product being equal to 0 means orthogonality, right? So in other words, this is saying that the T star minus lambda bar I of X, a vector, is orthogonal to V, right? Okay. Or in other equivalently, V is orthogonal to this vector. Okay. And here X is arbitrary, right? So the conclusion is that the vector V is orthogonal to the range of the linear operator T star minus lambda bar I. They're orthogonal to, let me write it fully. Yeah? So orthogonal to the subspace given by the range of this linear operator. All right, let me see. Question in chat. Should the definition in the previous slide change the variables? Which definition, sorry? Can you say what you mean?
Yes, I mean the definition.
Definition in the previous slide. Okay, so if I go here,
the first one, I recall one.
Txy, x t star y. Are you talking about this one?
Yeah, I'm sorry, I wrote down the variables wrong. That's why I was confused with the proof.
Okay. Well, I'm not sure. Just write later, okay?
Mm-hmm.
And I can try to answer. So, okay. So the vector v is orthogonal to this subspace. Okay. Are you with me so far? So why do we know this, right? Because look, no matter what x I take here, I get that v is orthogonal to the corresponding vector here, right? Now the range of this linear operator consists of all vectors of the form this linear operator applied to x, where x ranges over all vectors in V, right? So the previous line on the previous argument, this line shows that no matter what vector I take in the range, I get that V is orthogonal to it. Okay, so that's the point of this calculation. All right. So in particular, we have that V is not an element of the range of this linear operator, okay? Because V is a non-zero vector, and a non-zero vector cannot be orthogonal to itself, right? Remember, so it cannot be contained in the range, okay? So we get that the linear operator given by this expression, T star minus lambda bar I is not onto. Okay, because we found the vector not in the range. V is a vector not in the range of this operator. Okay, but now, because the dimension of V is finite, this implies that this operator is also not one-to-one. So this implies that T star minus lambda bar I is also not one-to-one. Oops, one-to-one. Right? Because remember, for linear operator on a finite dimensional vector space, these two conditions are equivalent, being onto or being one-to-one, right? All right. So it's not one-to-one. So what does it mean? It means that the null space is non-trivial, right? So, and I'm moving to the next page. We have that the null space of this operator, T star minus lambda bar I, is not equal to 0, right? We have some non-zero vector in the null space, okay? So take some vector like this. So take any W in the null space, which is non-zero, right? We just obtained that it exists. Then this means that T star minus lambda bar I applied to W is equal to 0, right? But what does it mean? So if we look at this equation, so this means that T star of W is equal to lambda bar times W. All right. So the conclusion is that W is an eigenvector of T star with eigenvalue lambda bar. Okay, so it's a scalar enough. Right? Okay. So this was the point, and we have obtained some non-zero vector, so that applying T star to it corresponds to just multiplying by scalar lambda bar. All right. So this gives us an eigenvector for the adjoint operator T star. Okay, and this was the motivation for. So you see, that's I guess the reason why we started with this operator here. Right, because the idea, remember, this is the same thing you use, for example, when calculating the characteristic polynomial, etc. So it's the usual point. We want that the null space of this operator corresponds to eigenvectors. So here we started with this for T, but then using the property of adjoints, we switched to the adjoint, and in the end we obtained that we get an eigenvector for the adjoint. So in all proofs, basically in all proofs, as this argument illustrates also, when you're trying to deduce something about the joint operator of a given operator, all you are given to use is this equality, right? This defining property that taking inner product like this equal to the taking inner product of the joint in the opposite order. So yeah. So that's always the main point for such arguments. Well, it's literally the only thing you can use, right? So we use it here, for example. Okay. So, all right. So this tells us at least that given an eigenvector for T, we can find an eigenvector for T star. All right. But we need some more information about what the joint looks like. So the next step is going to be the theorem 614. So often called so-called Schur lemma. So it's due to Schur. The situation is the same as usual. So assume we have T, a linear operator on V, where V is an inner product space of finite dimension. So the dimension of V is finite. Okay. And suppose that the characteristic polynomial of T splits. Okay. So assume it splits. Then there exists an orthonormal basis beta for V such that the matrix representing T with respect to beta is upper triangular. Okay. So remember, we know, for example, from earlier theorems that if we have a linear operator which splits, if we have a linear operator which is diagonalizable, then its characteristic polynomial splits, right? So we know this implication. So here we get something going in the converse direction, but not fully. So we get a weaker conclusion. But the idea is to collect as much information as we can from knowing that the characteristic polynomial splits. So of course, we don't get a diagonal matrix in general, but we get something useful. We get the upper triangular matrix in this situation. Okay. So let's try to prove this useful result. Okay, so proof. So we will argue by induction on the dimension of the space. Okay. So proof by induction on n equal to the dimension of V. Okay. So the case n equals 1, the base case. The base case is clear. Okay. So this is clear. Why? because any 1-by-1 matrix is automatically upper triangular, right? As any 1-by-1 matrix. So it's a matrix of the form just X for some scalar X, right? Is upper triangular. There's nothing to check here. Right. So remember, let me just recall. I assume you're all familiar with this, but upper triangular simply means that all entries below the diagonal are 0. Doesn't FT splits imply T is diagonalizable? No, of course not. That's the whole point. So I said that we have the converse implication. So T is diagonalizable implies that f of T splits, but the converse implication is not true. It's very important. So what we have, however, we try to get the best we can still from knowing that it splits, right? No, it's not if and only if. It's very important. I think I stressed it, but probably not enough. Yeah, it's an important thing to remember. That and I think when we discussed it, there should be counterexamples to it, or maybe I'll give you one later. So yeah, it's only one implication. But now we try to collect the best we can from knowing that the characteristic polynomial splits. So what it does give us is that we can find the basis, moreover, an orthonormal basis, with respect to which the matrix is upper triangular, okay? But not necessarily diagonal. Okay, so all right, so for n equals 1 is trivial. So suppose now, so we want to prove it, suppose that this claim holds for n minus 1, and we want to prove it for n. Okay, so the inductive step. All right, so what are we given in this situation? So in this situation, we assume that T is a linear operator on V, right? And the dimension of V is equal to n. So we're given this. And we denote f of T, the characteristic polynomial. Of T, and we assume that it splits, right? That's the assumption of the theorem. And f of T splits. Okay, so these are the assumptions for n. All right. So first of all, the first claim is that then T has an eigenvector. Okay, so this is the very first claim that we can deduce from this situation. Okay, why? Well, recall that this was, I think, by theorem 5.2. Okay, we know that lambda, a scalar lambda, is an eigenvalue of T if and only if it is a root of the characteristic polynomial. So if and only if f of lambda is equal to 0, right? Okay, but since we're assuming that f of T splits over our field of scalars f, okay, it has a root, right? Because remember, splits means it can be written as a product, right? So splits means it can be written as a product of monomials. So think of the form like some a minus ai product over ai minus T, something like this, right? Where ai is an element of the field of scalars. But then, of course, there is a root. So namely, I can take this coefficient ai, an element of f, then the whole product is going to be 0. So this is going to give me a root, yeah? So splitting over f guarantees that there is a root in f, okay? And hence, some eigenvalue lambda in f, right? So there's a root, so there is an eigenvalue, but then there is an eigenvector corresponding to it. So, and there is an eigenvector v in v corresponding to it. Okay. So at the very least, the characteristic polynomial splitting tells us that there is an eigenvector. All right. So I pause for a second, and I'm going to move to the next page. Okay, so all right, let's move to the next page. So far we have determined that there is an eigenvector. Now let's use the previous lemma, which tells us that then the adjoint operator T star also has an eigenvector. Let's call it Z, for example. Okay. And also normalizing it, we can assume that Z is a unit vector. A unit vector with some eigenvalue, let's denote it by lambda, yeah, with eigenvalue lambda. So the previous lemma tells us that if T has an eigenvector, then T star has an eigenvector. But if you take an eigenvector and normalize it, so multiply by 1 over the norm, you're going to get a unit vector, right? Which is still, of course, an eigenvector, but maybe with a different eigenvalue. Its eigenvalue is going to be multiplied by some scalar, right? But it doesn't matter. So we still have so the conclusion is that we get a unit vector, which is eigenvector, and we denote its eigenvalue by lambda. Okay. And now let's take W to be the span of this vector. So the span of Z. Okay. As usual, span is of any vector is of anything, of any subset is a subspace, right? So let's look at the orthogonal complement of W. So the next claim is that the orthogonal complement W perp is T invariant. Okay, so let's check this. Okay, so proof of the claim. Assume that Y is an arbitrary vector in the orthogonal complement. Okay, and assume that X is any vector in W. Okay, then by the definition of W, we have that X is equal to C times Z for some scalar C in F. Right, because W is simply the span of Z. So it consists of all the vectors of the form C times Z. Okay, hence we have, now we use the property of adjoints. So we look at T of Y inner product with X. Okay, what we're going to get is T of Y inner product with C times Z, right? Because that's the expression for X that we have. Now use the joint property. So this is the same as Y inner product with T star of CZ, right? But because T star is also linear, so remember the joint of a linear operator is itself a linear operator. So we get that this is the same as Y inner product with the vector C times T star of Z, right? But now this is equal to what? So we know that, remember, Z is an eigenvector for T star, right? So it means, and we know the eigenvalue lambda. We denoted the eigenvalue lambda. So then applying T star to Z corresponds to simply multiplying by lambda. So that we get that this is the same as Y, C times lambda times Z, right? So this is the expression for CT star of Z, okay? But now we can use the linearity properties of the inner product itself, right? So remember that if I take an inner product of a vector and multiplied by some scalar, what we get is the complex conjugate of the scalar C lambda complement conjugate, right, times the inner product of y and z. Okay, but remember that where did we take these vectors from, right? So we had y is an element of the orthogonal complement of w, right? And z is an element of w, right? So we have z belongs to w, and y belongs to the orthogonal complement, right? So this means that the product is 0, they are orthogonal. So we get C lambda times 0. Okay, and this is of course just 0 as well. Right? So why question, why isn't C conjugate when we took it out? Yeah, we have to take the conjugate. Let me see. Maybe I didn't write it correctly. Oh, but when we took it out, yeah, I did take the conjugate. So look, so far at this, okay, so this equality you agree. Now I evaluate T star of Z. So T star of Z is equal to lambda times Z, right? But then on the next stage, I just have C times lambda times Z, but C times lambda is an element of F. So it's just a scalar in F, right? So when we want to take the scalar out of the second coordinate, of the right coordinate in the inner product, we have to take the complex conjugate. So we take the complex conjugate, C lambda, complex conjugate of the product, because it's a scalar in F, right? And so, yeah, so we took it out, and then the inner product is 0. Does it make sense?
Yeah, I was confused about the first one where you took the C out of the T star, because I thought about theorem 6.11, the parts B. That's why.
Okay, hopefully. So, yeah, if not, let me know. So, all right. So at this stage, we have proved that, look, we have proved that if I take the inner product of Ty with X, I get 0, right? So it tells me that Ty is orthogonal to X, and X was any element in W, right? So the conclusion is that T of Y is orthogonal to every X in W, which means, of course, that Ty belongs to the orthogonal complement of W, right? And that's exactly what we wanted to show, because we started with Y in the orthogonal complement, W perp, and we have shown that then Ty is also in W perp. So this shows that W perp is T invariant, right? Okay, so this proves the claim that W perp is T invariant. Okay, so now we want to so let's continue the proof. So remember, our task is to show, to determine the matrix representing T and find the corresponding orthonormal basis beta, so that this matrix is upper triangular. Okay. So let's analyze further. So keep this claim in mind. We're going to use it soon. But for now, we need to collect some observations about the characteristic polynomials. So first of all, okay, so excuse me. So we have the following claims at this point. So first of all, we know that the characteristic polynomial of T restricted to the subspace W perp divides the characteristic polynomial of T. Okay, so remember that taking restriction to an invariant subspace, the characteristic polynomial of this restriction divides the characteristic polynomial of T, right? This was theorem 521. Okay, so it divides, but T splits. Okay, so and T splits by assumption. So we conclude that T W perp also splits. Right, because if I have, if I can write F, the characteristic polynomial of T, as a product of linear factors, and linear monomials, and then TW perp divides it, so it's just the product of some of those monomials. But this means it splits as well. Yeah, so we know that this restriction splits. Okay, we also know by theorem 6.7c, so look it up, we can, this is a theorem which tells us that the dimension of W perp and how it's connected to the dimension of W itself and the dimension of the whole space, right? So the dimension of W perp, remember, so we can calculate it as the dimension of V minus the dimension of W, right? Because we have the W is given by the direct sum of W, V, excuse me, let me write it. So remember, V is given by the direct sum of W and W perp, right? So then the dimension of V is the sum of the dimension of W and W perp. So then to determine the dimension of W perp, I just subtract like this. Okay, so this is the dimension of V minus 1, right? Because W is generated by a single vector, remember. W is the span of Z minus 1. So this is N minus 1, right? The dimension of V is N. Okay, so you see, maybe this is promising because we have found some space, W perp, whose dimension is smaller than N. So maybe this gives tells us now we can try to apply the inductive assumption to it, right? Okay, so by the inductive hypothesis, applied to the linear operator TW perp on the subspace W perp of dimension N minus 1, we obtain an orthonormal basis let's denote it gamma for W perp, such that if we look at the matrix representing T W perp with respect to gamma, then this is upper triangular. Right? So since it's a smaller dimensional subspace, I could apply the inductive hypothesis to get such a basis gamma with this condition. All right. So the next task is now to connect the matrix for this restricted operator with the matrix for the whole operator T. Right? Okay. So let me pause here for a second before I move on the new page. So at this point, all you have to remember now is that we have this restriction TW perp, and we have found that it's a basis for it, gamma, which gives us triangular matrix, upper triangular matrix. Okay. So now we take beta to be gamma together with Z. Okay. So I add Z to gamma. First of all, this is still an orthonormal set. So then beta is an orthonormal set, right? Because remember, Z belongs to W, and gamma is a basis for W perp, right? So gamma is a subset of W perp. So it means that Z is orthogonal to gamma, right? And gamma is orthogonal. So we conclude that then beta is orthogonal. And we also chose Z to be a unit vector. Okay, so combined, this tells us that beta is also an orthogonal vector. Set, sorry, excuse me. So beta is an orthogonal set. Moreover, it's orthonormal because gamma was orthonormal and Z is a unit vector, which is orthogonal to everything in gamma, right? Okay, so we see that this is an orthonormal vector, In particular, it is, I keep saying vector, sorry. This is an orthonormal set, okay? But we know that then beta is also linearly independent, right? Because remember, orthogonality implies linear independence. This was corollary 2 of theorem 6.3. Okay. So beta is linearly independent and is of size n, right? So of size n equal to the dimension of V. So the conclusion is that beta is an orthonormal basis for V. Okay, so what remains to show now is that this beta actually works. So the matrix representing T with respect to beta is upper triangular, yeah? The last step. Okay, so let us denote gamma. So we already given gamma, right? Let me write gamma, list the vectors in gamma as d1 through zn minus 1. Okay, so just list the vectors of gamma in this or in some order like this. Well, in a given order, I mean, because gamma is an ordered basis. Okay, so we have, now we'll look at the matrix representing T with respect to beta. Okay, so first I just spell out the definition as usual. So the columns of this matrix are of the form T z1, the coordinate vector with respect to beta, etc. Then we have the column corresponding to the coordinates of T, Z, n minus 1 with respect to beta, right? And finally, we have the final vector. So we have T of Z with respect to beta, right? Because beta, once again, beta consists of Z1 through Zn minus 1 and Z, right? Because remember, beta is the union of gamma with Z. Okay. So now, what do we know for this? So for the first n minus 1 columns, we know that they are all in W perp, right? So it means that the last entry has to be 0. So we get the first column can be replaced by T of Z1 with respect to gamma, and we have 0 in the last entry, right? Similarly, we have here T of Z n minus 1 with respect to gamma and 0 in the last entry, right? Because again, all these things leave, because Zi is in W perp, and W perp is T invariant. So we know that T of Zi is also an element of W perp, right? And Z is the vector in the basis, which is outside of W perp. So we get this, and the last column remains unchanged. Yeah. So here we have nothing else to add. We just have TZ beta, the whole column. Okay. But now, what is this? So this is given by the block representing T W perp with respect to gamma, right? So this part, this is just the matrix representing T with respect restricted to W perp with respect to gamma. We have a bunch of zeros here, and we have the final column T of Z beta. Okay, and remember, we know that T W perp gamma is upper triangular. Okay, remember we had this by the inductive assumption. So this follows that the whole matrix is upper triangular as well. So thus T beta is also upper triangular. Right? So to see this in the picture, look, we have the diagonal of this matrix, right? And we have zeros everywhere under the diagonal. And so, and we have just one final entry on the diagonal, which comes from the last column. But this entry we don't care. because we only need zeros below the diagonal. Yeah. So we have that, we have zeros everywhere below the diagonal then. So which means that the whole matrix is upper triangular. All right. So this concludes the proof. This concludes the inductive step, and hence the proof of the whole theorem of Schur. So yeah. So I'll stop here today. We see this. This is a next best thing after the converse that we discussed earlier, which is not true. But this is something that is true. So if the characteristic polynomial splits, you don't necessarily get a diagonal matrix with respect to some bases, but you get the next best thing, which is upper triangular, which is also helpful, right? Like for calculating determinants, for example, etc. So okay, so far we know this, and next time we'll finally figure out what was the question marks. Remember, so what corresponds to the existence of an orthonormal basis of eigenvectors? Like what is this strong condition which guarantees us that property? Okay, so that we'll discuss next time. I'll stop here today. Yeah, thank you very much.